Right, welcome back. So we've got our first and second laws of thermodynamics down in local form, right, over the spatial configuration. And what we're going to do now is introduce a new concept in this mix. The way we're going to do this is through an argument that has both mathematical and physical aspects. So let's start on a new sheet, on a new slide. Right. So the topic of this segment is the Legendre transformation. Okay. And what this transformation is going to give us is something called the Helmholtz potential. Okay, let's start with the physical aspect of it. Let's talk a little about constitutive forms here. So far, in our treatment of thermodynamics in the context of thermomechanics, we've introduced three new quantities, right? We have E bar, the internal energy, per unit mass, we have eta bar, the entropy per unit mass, and we have theta, the temperature. Now, when I put down the internal energy, I said that this is really the energy of the body. And I mentioned back then that even our notion of strain energy that we've encountered previously resides in the internal energy. Okay, so this contains it contains strain energy, and of course, since we're talking about thermal aspects now, it must also contain some aspect of thermal energy, okay, whatever that means for now. Okay. Now, again, if one goes and studies thermal physics and statistical mechanics from fundamental ideas, you consider systems and the states available to systems and so on, what one can show is that the proper rigorous postulational basis of thermodynamics, or at least one rigorous postulational basis of thermodynamics, develops as follows. E bar is a function of quantities that I am going to write as this, our Green-Lagrange strain tensor. Okay, this is where the strain energy comes in. As far as the thermal fields are concerned, E bar is properly a function of the entropy. So the idea is that in some sense the entropy is a representation of the states available to a system, and the energy in the system is determined by the states available to it. Okay, so E bar is a function of eta bar, and there are rigorous ways of explaining this. I should also mention that all of these variables on this, all the quantities in this equation are so-called extensive variables. Okay. So, well, the strain is not really an extensive variable, but it's derived from an extensive variable. So, well, I'll just state that, and I won't write it down because if I write it down, I'll have to start justifying it and all that. But and we just really don't want to go down that path. Anyway, this is what we have. Okay, so this can be obtained. This can be formally obtained. More importantly than formally, can be rigorously obtained from rigorously defined in thermal physics. Okay. Okay. Anyway, this is the constitutive description we have, right? E bar is a function of the Green-Legendre strain and eta bar. Now, so the strain is all very well, but it turns out that for most systems, the entropy is not always a convenient quantity to work with. Okay, and therefore there is a reason to come up with a different quantity. Okay. So let me state that. What we want to do is we want to reparameterize with another quantity in place of entropy, and in particular, we want to reparameterize with temperature in place of entropy. Okay, and the reasons for this are sort of the physical and the physical reasons for this are that the temperature is just a little easier to measure. It's understood better. It's an easier quantity to work with, right? And so it's often easier to access. The convenient aspect of this is that it turns out, right? Again, from thermal physics. Okay. From thermal physics, the temperature is can be shown to be defined as the derivative of E bar with respect to eta bar. Okay, and this is also rigorous. In fact, this is actually the way the temperature is even introduced in the context of thermal physics. Okay, so what does this mean? What this means is the following. So supposing we were to think of this sort of a graph, right? The strain is not in the picture right now, right? Of course, E bar depends upon the strain, but imagine that we're just plotting up E bar with respect to eta bar. Suppose we have this sort of a curve for it. Okay, theta, as defined here, as you can see, is the slope of the tangent to this curve, right? Right, by definition. Okay. Now, if we want to go away from this description of an energy that is parameterized by the entropy, here is what we can do. Okay? And in order to show you what we can do, I'm going to go to the next slide and redraw this picture. And I'm going to try to draw it a little bigger because I want to do certain things with it. So I have this again. And let me extend this axis down. Okay, so we have this curve which is eta bar as a function of, yes, we have the strain, but the strain is really not of interest right now in these arguments. Let's talk about eta bar. Now, the whole idea is that if we choose a point with a particular value of eta bar, let's call this eta bar 1, and we look at the corresponding value of E bar, Let's call this E bar 1. Okay. Let's consider the tangent to the curve, right? This is theta. Now let's consider extending this thing all the way back until it intercepts the E axis, the E bar axis. Okay, so this, as we know, is theta, which is this derivative evaluated at eta bar 1, right? Now, here is the idea. If we want an alternate parametrization of our system instead of E bar depending upon eta bar, we can do so by looking at what we have on this graph. And in particular, we could say that instead of using combinations E bar 1 and eta bar 1, okay, we can replace these with the idea of the slope at that point, right? And let me just call this theta 1. Okay, let me just denote that as theta 1. We can replace it with the slope at that point to the curve, as well as the as well as the intercept along this axis. Okay, so the intercept along this axis is this quantity, right? It is right. We could look at this quantity. Okay, right? And this quantity, if you observe, for the way we've written things out, is E bar 1 minus theta 1, right? Because theta 1 is a slope, right? Theta 1 times eta 1. Okay? Right? So the idea is that this value, the value here, how do we get to it? We get to it by looking at E1, okay, and subtracting from it, right, the value of that much. Okay, because when we get to it, we get to this point here. Okay, this is a simple construction just using the idea of a straight line. Okay, what we're doing here is to write out that point by starting at E bar 1 and subtracting from E bar 1 the quantity that I've put a brace on. Okay, that quantity that I've put a brace on is theta 1 eta 1 bar. Okay, so what we have now is is this idea that instead of going with E bar 1 and eta bar 1, we could replace it with theta 1 and, because I need more room, let me do this. We could replace it with this quantity E bar 1 minus theta 1 eta bar 1 and theta 1. Okay, what we're doing really is to replace, instead of going with the points E bar 1 and eta bar 1, we are going with the intercept on the ordinate and the slope to the same curve. Okay, now if we do this for another point, right, if we call this point eta bar 2 and E bar 2, we can carry out the same construction. This is my tangent. I extend the tangent back. Okay, that slope by definition is theta 2, right, which is just the derivative of the E bar eta bar equation with respect to eta bar at that point. Okay, and then we see that this point here is E bar 2 minus theta 2 eta bar 2. Okay? Now what you see is that if at every point we construct these tangents, we will get the envelope to this curve, right? Because at some other point we will get that tangent, right? The tangent at that point and that intercept, right? And so on and so forth. As we complete these tangents, we basically we reconstruct the envelope to that curve. Okay? So in general, if we replace E bar and eta bar, right, which are really the coordinates of points on the curve, we replace them with the intercept on the ordinate. The intercept on the ordinate is E bar minus theta eta bar, and the slope. We reconstruct the curve by obtaining the envelope to the curve using each of these straight lines. Okay, so these are the coordinates, and these together give us the intercept and slope, which then lead us to the envelope to the curve. So the envelope to the curve given to us by the intercept and the slope give us an alternate way to represent the slope instead of the coordinates themselves. Okay, there's no new information in the system. It is just a different way of representing the same information. Okay, and this gives this sort of a transform is what is called a Legendre transformation. Okay, so mathematically, this operation is called a Legendre transformation. Okay, where we go from E bar eta bar to E bar minus theta eta bar, right, where theta is the slope to the curve, right, the tangent to the curve, and the slope itself. Okay, so with we have the intercept and the slope. Now, for convenience, this quantity is denoted, I'm going to use our same notation. Maybe I should not use the same notation. Let me use something else here. I need to think of a symbol we have not used too much yet, so let me call this chi. Chi, okay, and theta. So that's chi. This quantity chi, which is defined as E bar minus theta eta bar, this quantity is called the Helmholtz potential. Now, with this Helmholtz potential, it is parameterized instead of eta bar by theta. Okay, so properly stated, we have chi now function of E, because nothing happened to the strain in this whole argument, and theta, okay, and this is defined as E bar, which is a function of E, and eta bar minus theta eta bar, okay, where we know that theta is that derivative. All right. Okay. Now, this quantity chi is sometimes also called the Helmholtz free energy. It's called the free energy because there are other interpretations which work out to an understanding that chi represents the amount of energy that we can actually extract from the system. Okay, the amount of sort of usable energy, useful energy that we can get out of the system. So it's sometimes called the free energy. But really, properly, it is just a potential. Okay, so I think we're going to stop here.